We know that machine learning algorithms are divided into three broad categories: supervised, unsupervised, and semi-supervised. Naive-Bayes is one of the simplest supervised learning algorithms which is primarily used for text classifications, and it works really good with high dimensional data. It is based on the Bayes theorem with the primary assumption that the input features being used are independent of each other and each feature has an equal contribution to the final output. It is a probabilistic classifier, which means it predicts on the basis of probability of an object. And some popular application of naive-Bayes algorithms are spam filtration, sentimental analysis, classifying articles, etc. In this video, we are going to understand what naive-Bayes is, how it works using an example, and we shall also see the implementation of naive-Bayes in Python using scikit-learn. I am Saurav Agarwal, you are watching Datahat Unfolding Mystery. Let us understand the theory behind naive-Bayes. So one of the primary things to understand that naive-Bayes, being based on Bayes theorem, holds two underlying assumptions. First, the variables or the input features being used are independent of each other, and secondly, each feature has equal contribution to the outcome. We must understand conditional probability in order to understand naive-Bayes or Bayes theorem. We created a separate video based on likelihood and probability, wherein we understood what is the difference between likelihood versus probability. A probability denotes the chances of occurrence of an event, whereas likelihood denotes, given the outcome to be true, what are the chances of having the particular set of values for our set of parameters. For example, given that the class is C1, what are the chances that our parameter x will have value equal to x1? Okay, hope this is making sense. Conditional probability, on the other hand, is based on the idea that given a set of given the set certain situation, or given that certain event has already occurred, what are the chances of event B to occur? It's kind of like, given that event A has already occurred, what are the chances of event B to occur, which is given as probability of B given A. Here, probability of A given B denotes, given that event B has already occurred, what are the chances that event A will occur. So, as you see, the conditional probability, or here the Bayes theorem could be written as probability of A given B is equals to probability of B given A into probability of B given A into probability of A by probability of B, which tells us how often A happens given that B has already happened, written probability of A given B. It is also known as posterior probability. When we know how often B happens given that A happens. Let me read this out statement and then I'll explain you what this means. How often A happens given that B happens, written P of A given B, also called posterior probability. When we know how often B happens given that A happened, written probability of B given A, and how likely A is on its own, written P of A, and how likely B is on its own. So understand, we are computing here the probability that event A will occur given event B has already occurred, denoted as probability of A given B. It is also known as posterior probability. How we will use it in terms of our classification? Assume that we want to determine what label or what class would our set of inputs would belong to. Say our input variables are denoted as x1, x2 and x3. So given that we already see x1, x2, x3, what are the chances or what is the probability that our class is C1? Okay, so here y equal to probability of y equal to C1 given x equal to x1, x1 equal to capital X1, x2 equal to capital X2 and x3 equal to capital X3, as you can see in the image here. Now Bayes theorem is used to determine the probability of a hypothesis with prior knowledge. So understand that all classifications are based on hypothesis, which means based on the certain statistical parameters, we estimate what is the chances of having a particular class as our outcome. Okay, hope this is making sense. So as you see, as the example that I was already talking about above, you can see it here once again. Probability of y equal to k. Here y is our class or target label, and given the set of input features capital X1, capital X2, capital X3, or so on up to xn, this would be denoted as probability of x1 given y equal to k multiplied by probability of x2 given y equal to k, and so on and so forth based on this equation. Now why we are having such an equation? Because on the Bayes theorem we applied certain assumptions. If we did not had those assumptions, we would follow the chain rule of conditional probability. The link to which can be found, I'll attach the link to understand the chain rule of conditional probability, but we do not need to go into that details. Just understand that in order to make use of the naive Bayes, you need to understand this formulation. That's it. Now let us also see the working of naive Bayes through a case study. We have a data set consisting of the weather reports: rainy, sunny, overcast, overcast, sunny, and so on and so forth. So we have one feature. The output is denoted as play, whether that individual will go out to play or not. So we first convert this given data set into a table of frequencies. Okay, let us see what is table of frequencies here. This is our table of frequency. For overcast, we have 5 yes, 0 no's. Rainy, we have 2 yes, 2 no's. Sunny, we have 3 yes and 2 no's. The total of yes is 10, the total of no is 4. Okay. Now, the next thing that we need to do is we generate the likelihood table by finding the probabilities of given features. Now, you remember, like, what is likelihood? That given our class label is already true, what are the chances of observing certain values for our parameters? So assuming that our class is already C, what are the chances of observing parameters X? So we are computing this on the training set. Okay, how we are computing this? The likelihood table will denote something as this. Given, see, overcast, given that our class is yes, the likelihood of observing overcast is 5 by 14. Okay, why 5 by 14? Because the total is 14. 5 plus 2 plus 3 plus 2 plus 2. We have total of 14 cases. Now given, given that, as we'll see here, wait 1 second, yes. So given that our class label is yes, what is the probability of it being sunny? It is 3 by 10. Similarly, given that our class label is yes, what is the probability, what is the likelihood of having overcast is 5 by 10. Okay. So on and so forth, as you can see from the table here. So applying naive Bayes, we compute our probability of the class label being yes given sunny. Similarly, probability of no given sunny. So whenever you have certain input, say you have the input as overcast, so what is the probability of the individual going out to play given it is overcast? You can compute it here. Let me know in the comments what are your answers. The question, the assignment question remains as, given that the weather is overcast, what is the likelihood or what is the probability of the individual, or let's say the individual is Sam, what is the chances that Sam will go out to play? Okay, let me know in the comments. Now that you understand how do we apply naive Bayes in the form of an example, I am sure that you will be able to solve the equation and let me know in the comments. We shall now look at the types of naive Bayes classifier. So primarily naive Bayes classifier is categorized into three types. Now this three categorization depends on how we embed our text features. Here remember we could either convert it into one hot encoding, frequency based encoding, word encoding, or various other encodings that are available. We shall go into the details one by one. So there are three primary types of naive Bayes classifier: Gaussian, multinomial, and Bernoulli. Okay. So if the input features are continuous values, or if we can say if our input is a set of real valued features, then we will consider Gaussian naive Bayes. If the input features denote frequencies for certain values or certain values in the features, then we shall use multinomial naive Bayes. Whereas if the input features are one hot encoding denoting either true or false values for each feature, then we shall use Bernoulli based naive Bayes classifier. The implementation for all these three are available under the scikit-learn package, the link to which would be attached in the description of this video. Now we shall look at the advantages and disadvantages of naive Bayes classifier. So naive Bayes classifier is a quick to use or computationally less expensive model. It is suitable for solving multi-class prediction problems. At the same time, it has the advantage of working with high dimensional dataset. As you understand, text dataset is usually having a large corpus, and the dimensionality in text based problems or NLP based problems is large. So naive Bayes classifier is able to handle larger dimensionalities. Naive Bayes is better suited for categorical input variables than numerical variables. So here to understand that multinomial naive Bayes is more suitable or more better designed to function compared to the Gaussian naive Bayes. Disadvantages. So some of the disadvantages of naive Bayes is that its underlying assumption. So it has a high bias. Assuming that each of the input features are independent of each other is very rare to find in our real world space. So that in the assumptions at many times in our real based world scenarios do not hold true, and our performance is not as expected. The algorithm faces the zero frequency problem, where it assigns zero probability to a categorical variable whose category in the test dataset wasn't available in the training dataset. So understand this thing. Say for example, there is a particular level, a particular category in a feature which is not available in your training data set. It would be assigned a probability of 0, and your entire output, since it is a multiplicative formulation, so your entire output would sum to 0 probability, right? If you multiply multiple quantities and if any one of the quantities is 0, then the entire equation becomes 0. So that is another disadvantage. So hope this is making sense and hope you are understanding naive Bayes algorithm. It is very simple and very easy to understand. Another disadvantage is, sorry, it's not a disadvantage, rather we shall one of the fixes to the zero frequency problem is smoothing. So whichever label, or like what we do is, for all the categories that are present, we assume that there is one additional value for that category present. So even if the category is not present, it will still have a non-zero probability, because instead of having 0, we are adding a constant 1. Okay. You don't need to go into the details of it as of now, just understand from interview perspective that what is zero frequency problem and how can you fix it. So you can fix it by smoothing. One of the smoothing techniques is Laplace smoothing. Applications of naive Bayes. So naive Bayes can be applied to a multitude of problems, multitude of supervised classification problems, especially the text-based classification problems such as credit scoring, spam filtering, sentiment analysis, real-time prediction, as it is an eager learner, right? What do we mean by eager learner? That all the computations, all the likelihoods are computed at the training time and stored. You are not making any further computation during prediction. So in real-time prediction scenarios, this becomes very handy. We have also provided an implementation using scikit-learn. Okay, you can go through this implementation and understand how to apply naive Bayes in Python using scikit-learn package. As the sample data set being used here is the iris data set. We have the X, the data the features, and Y, the target labels. We are splitting it into train test split, and we are applying Gaussian naive Bayes here. Okay, the metric being used here is the accuracy score. However, in classification problems, accuracy score is not the very reliable measure, not a very reliable performance measure, but for the case of understanding and keeping things simpler, you can work around using this accuracy score. The other metrics to use is, like for example, in a binary class setting, you could use ROC AUC score, or you could use log loss, or any other loss metrics, which we shall cover in detail in our video lecture covering the loss functions. Okay, hope this is clear. Hope you understand now what are the different nuances around naive Bayes, how to implement naive Bayes, what is the working around naive Bayes using an example, and don't forget to share your answers regarding the assignment question. If you are new to the channel, don't forget to subscribe, hit the bell icon, share it with friends and data science enthusiasts. See you in the next lecture. Have a nice day. Bye bye. Jai.